Hello coders! In this video we are looking at a straightforward approach to Advent of Code 2022, day 14. This puzzle should be approachable by anyone who has learned the basics of coding. More specifically, this guide uses Boolean logic, sets, arrays, loops, and custom data types. That's it. There's nothing fancy here. By the end of this guide, you will have a working solution for the first part of this puzzle. Although I won't provide a step-by-step guide for part 2, at the end of this guide I will give hints and discuss a high-level approach for adjusting your solution to solve it. I've posted a link to the puzzle in the description below. If you get stuck, don't hesitate to post your questions in the comments or make a post on the Advent of Code subreddit. There are a ton of people there that would love to help you out. And of course, if you find this guide helpful, let me know by clicking that like button. And if you want to see more Advent of Code guides, be sure to subscribe. With that, let's get into it. Following the distress signal, you find a giant waterfall. The signal is coming from behind it. Upon closer inspection, you find there is a large cave system here. You swallow hard and muster up the courage to make your way deep underground. Without warning, the ground begins to rumble and sand begins pouring into the cave. You must quickly find a safe space to avoid being buried alive. Can you write a program to analyze how the sand will fill the cave? Captain Coder here with day 14 of Advent of Code 2022. And we just can't seem to catch a break. As you heard, we are about to be buried alive unless we can find a safe place to escape the falling sand. In my opinion, this puzzle is so fun. We are asked to write a simulator modeling how sand will fall into this cave and pile up. But before we hop into it, we should break down what the problem is asking, understanding what our inputs are and what our output should be. In this puzzle, we are receiving instructions describing line segments in a two-dimensional grid representing a cave structure. For example, if we scroll down a bit here, we see our inputs here. This is one chunk of lines. This is a second chunk of lines. And this little picture here in this ASCII art represents this cave. So we have a line going from 498,4 to 498,6. So we look over here, we have 498,4 down to 498,6. So that's this vertical line segment. Then we go from 498,6 to 496,6. And so that's this line segment here. If we look at the next one, we have this line segment and it comes out here 2 spaces, goes down and then across, forming our cave. We are also told that the sand falling into the cave begins at position 500, 0. This is a constant in our program. We will always have sand pouring in from this location. Next, if we scroll down, we are given instructions on how to simulate the sand. The sand falls 1 grain at a time, which is much less daunting than the problem description seems to suggest. To determine where the grain of sand will land, we follow 3 rules. If there is nothing below the grain of sand, it moves downward. If it's as far down as it can go, it tries to move down and to the left. And if it can't go down and to the left, it tries to go down and to the right. That's it. If we follow this example here, we see that the first grain of sand will land directly beneath on this rock here. The second grain of sand is going to follow the exact same path, but when it reaches this position, it can no longer go down, but it looks down and to the left. That space is not occupied, so it fills it. If we continue here, the next grain of sand is going to fall and go to the right. That's this one. Then this grain of sand is going to come in. It's going to come here and it's going to see that it can't go down, down left, or down right. So it's going to stick. We'll get one more piece that's going to fall down. It's going to stop here. It's going to see, oh, I can't go down, but I can go down and left. And then it's going to go down and left again to this space here. If we continue, we eventually will end up in a state where our sand is falling off the edge of a platform into the abyss. The first time this happens, our simulation stops and we're done. What is the problem asking us to produce? We need to run our simulation. Then when it's done, we count the amount of sand grains that are in our environment, and that's the number we report. Not too bad. Now that we have a better understanding of the puzzle, let's talk about a strategy. First, we need to come up with some data types. We are going to define a position data type representing an XY coordinate. And second, we're going to define a cave data type to represent the puzzle's input. With those two types, we have enough information to represent our puzzle, so we're going to go ahead and parse it in. After we have this, we're going to define a sand type to represent a path that a grain of sand will take when falling. And finally, with these three types in place, we can solve the puzzle by running our simulation until we have met the end condition. Once we've met that end condition, we simply count the grains of sand and report it. Are you ready? Let's go. The first thing we're going to do is define a simple position type. This is a type that's going to represent an X and Y coordinate inside of our cave. And for convenience, I've added in three properties that are getters here to get a position that is down. So the Y position is increased by 1. Left, the X position is -1 and the Y position is increased by 1. And down right, where the X position is increased by 1 and the Y position is also increased by 1. One thing that you're going to want to keep track of here is that Y is going down, not up. Also, I have defined a parse method here for my position. This is going to be how I construct this using my input. The string that's going to be passed in here is going to contain two values that are strings separated by a comma. This is the coordinates that are going to be passed in. The left side represents the X position and the right side represents the Y position. To give myself confidence that I have successfully implemented this method, I've written a test here. That test, when I parse a string 12,7, that I get back a position 12,7. Similarly, I've done this with position 00 and position 490.63. Go ahead, write yourself a test, write yourself a parse method, and for convenience, give yourself a down, down left, and down right getter. If all went well, you have a passing parse test here. Mine's passing. If you're not quite there yet, go ahead and pause and I'm going to show you my solution. Here we are in position. Relatively simple. I take in the string that's being passed in. I split it on the comma to get back the left and right token. And then I simply parse those as integers. So I take the first token, pass it into the X position, and the second token and pass it into the right position. Before we move on to defining our cave type, I would like to define a helper function build segment, which is going to make it easier for us to build the segments that are defined in our input. In this case, I have defined a function called build segment that accepts a starting and ending position. It then returns a set of positions. You can use a list here if you'd like, but the reason I've chosen a set is because we would like to be able to quickly determine if any position happens to be inside of that segment. This will be useful when we're testing whether or not our grain of sand can move into a position. If you use a list, you have to iterate and search the entire list to find a position inside of it. However, sets have the property of having a very quick lookup for finding if a position exists inside. The build segment function should work in the following way. You need to make sure you add both your start and end position, and then determine all of the positions in between. To give yourself confidence that your implementation works, I always recommend writing tests. So let's look at this test build segment here. I have actually taken each of the input segments here from the example and added them in as tests. So if I start from 498.4 and go to 498.6, if I call build segment, I should get back a set that contains the start, the position between those two, and the end. So this will test that I'm going horizontally correctly. I also test that I can do vertical line segments here, as well as segments that go right to left and a long line segment. Go ahead, write yourself a test, see if you can write an implementation that passes that test, and as always, good luck. I'm happy, all of my tests are passing, and I'm about to show my solution. If you're not ready, go ahead and pause. Here it is. Build segment takes in a start and end position. I initialize my set, I add my start to the set, and then I want to loop until I've reached the end position. To do this, I calculate the difference in X and Y position and set it to either be +1, -1, or 0. That's what this helper function math.sine does. It takes the value of the expression here and reduces it to the sign, either -1 or +1. Then I calculate a new position from my start, adding in that difference. Because we know these line segments are only vertical or horizontal, one of the diff x or diff y will be 0 and the other will progress in the correct direction. Finally, I add that to my set and continue looping until I've reached the end, and finally return that set. Next, let's talk about our cave type. How are we going to represent our puzzle? In this case, I'm going to recommend the following structure. We're going to have a set of positions representing where our rocks will be. Again, I'm using a set to have quick lookup times for checking if a position is a rock. You can use a list, but a list will be a bit slower because you have to scan the list to search for an element. Sets have a property of having very quick lookup times. I'm also going to need to know where the bottom Y position of my cave is. Additionally, the origin is a constant position at position 500, 0. And we also need to know which positions contain sand. So I've also added in a set for settled sand. Once again, I'm using a set to have very fast lookup times. With a cave structure in place, we are going to write a print window method on a cave, which is going to allow us to get a string that visualizes a specific location within our map. This is going to take in a position for the top left of the square we're going to draw and the bottom right of the square we're going to draw. This will need to loop through all of those positions that are found within this and add them to our string. I recommend constructing it row by row. To help with this, I've defined a method, position to symbol, which given a position returns the character we should put in that position. If our set of settled sand contains that position, we're going to represent that with an O, just like our example. If it is a rock, we're going to represent it with a hash. If it happens to be the origin, we're going to represent it with a plus. Otherwise, it is open air, so we're going to represent that with a period. And of course, I've written a test here to give me confidence that my print window method will turn a valid string. In this case, I've taken the inputs from our puzzle and added them in here. So this is the initial state of the cave we are given in the example. I've gone ahead, built up a set of rocks using my build segment method. I've constructed the cave specifying that the bottom's at position 9. And then I call print window with the top left position 494, 0 and position in the bottom right 503, 9. I determined this by looking at this picture here. Then I check, is the string returned by my print window the same as the expected value? I also do a test where I add sand in specific locations and check that the print window is returning the proper string. And I do this several times just to make sure it's working as expected. As always, I highly recommend you write a test, then implement your function, and finally validate it against your test. Ideally, you have a print window function or method that is generating a string that you're happy with. If you're not quite there yet, go ahead and pause, and I'm going to show you my solution. Here I am in my cave. I take in my top left position, my bottom right position. I initialize a string that's empty. Then I loop row by row. So Y is row by row. I start Y at the top left Y, and I stop when I get to the bottom right Y. A lot of times this can be a little tricky because you're used to writing for loops that are less than the length of your input. In this case, we're going to be less than or equal to the length of our input. Next, I do the same thing for my X. This is my column. So I go row by row and column by column. I construct a position at that XY coordinate. I call my position to symbol to get the correct symbol out, and I append that to my cave string. Once I've finished a column, I add a new line at the end. And once I have finished looping through the entire structure, I return cave, but first I trim it to remove any extraneous white space from the front or end. With a cave data structure that represents our puzzle state, we're ready to parse it in. I've gone ahead and written a parse function here that takes in an array of strings. This is going to be each row of input, and returns a cave. You're going to need to build up a set of occupied spaces, as well as determine the bottommost Y position, construct your cave, and return it. To give yourself confidence that your implementation works, I always recommend writing a test. Let's take a look at how I've written my test here. I've taken the example input and added it in here. I then call my cave's parse method. For ease of testing, I'm going to use my cave's print window method because I have confidence that it works from my previous test. I call print window to get a string. Then I compare that string against the expected outcome from our puzzle description. Go ahead, write yourself a test, write your implementation, and see if you can get it working. If all went well, your test is now passing and you have confidence that your parse method is working. If you're not there yet, go ahead and pause. I'm going to show you my solution. Here is my solution. I start by initializing my occupied set to be empty. I set my bottom Y to be 0. That's the topmost position. I loop through each of my rows of input. I split that row on an arrow with a space on either side. That's what our input has. We have a delimiter here that is an arrow with a space on either side. Then I'm going to loop through those positions. I need to take each pair of position, the left position and the right position, and iterate down. I'm always looking at 2 positions. So rather than iterating all the way to the end of my list, I go to the end of my list -1 because I'm going to access 2 elements. I then extract the start and end position using my parse function. I update my bottom Y position to be the max of what bottom Y currently was and the Y position of the start and end that I just parsed. Next, I build my segment of positions using my positions build segment function. And finally, I union that set of positions with the occupied set. Union is the process of adding together both sets. Once I've finished this iteration, my cave is complete, I construct it, and I return it. With a cave structure in place, we are now ready to simulate sand falling, a single grain of sand. To do this, I'm going to define a type called sand, which has two properties. It's going to have a position, which is its current location, and a cave, which is the cave that it is falling in. Next, I'm going to define a method called fall, which will cause our sand to move one position following the rules down, down left, or down right. If the sand is able to move, it will update its position and return true. If it's unable to move, it will remain unchanged and return false. As usual, I've gone ahead and written a test. In this test, I'm using my parse method to load in the example cave. I've written my parse test, so I have confidence it's going to work the way I expect it to. This comment here represents the model I'm expecting the cave to have to give me a better idea of reasoning about it and talking you through how my tests work. I'm going to start by creating a grain of sand at the start position. This is the origin in our cave. Next, I'm going to call the fall method on that grain of sand. Falling should move it south 1, down in the Y direction. Since it moved, it should return true, and the Y position should update to be 1. If I call fall again, it will continue falling down and returning true, updating the position as we go until we arrive at position 500,8. At this point, the fall method should return false, indicating that the sand could not move and the position should not change. To continue our test, I've gone ahead and added that grain of sand's position into our cave's settled sand. After adding that, our picture should look like this, with a grain of sand added at position x equals 5, y equals 8. Because I know the next grain of sand is going to follow that same path, I create a new grain of sand that just happens to be one above it, and I check its fall method. It should return true because it should fall to the left. I check that the position is now 499,8, and that if I call fall again, it cannot move. It should have settled because there's floor in all three positions beneath it. I continue this process. I add a grain of sand above and check, does it fall to the bottom right? I add a grain of sand back into that position one more time and I check, does it fall? It should report, no, it doesn't fall. The grains of sand should prevent it from falling left or right or down. I do one more check, adding a grain of sand just above that one. This grain of sand should fall twice, down left and down left. To give yourself confidence that your implementation works, I highly recommend writing a test like this, writing your implementation, and then doing your best to iterate until your implementation passes. Go ahead, give it a try. I hope that wasn't too painful. I hope you have a passing test. If not, go ahead and pause. I'm going to show you my solution. Here is my solution. My fall method works in the following way. I check, is the position below this occupied? If it's not, I set my position to be the position below this and I return true. If that position was occupied, I continue and I check, is the position down and left occupied? If it's not, I update my position to be down and left and return true. If it is occupied, I have one more check. I check, can I go down and right? If I can, I update my position to be down and right, and I return true. And finally, if none of these conditions were met, I return false, saying that I wasn't able to update my position. You may have noticed I added in a helper function here, is occupied. Let's go look at that. It's part of my cave class. Nothing too crazy. I simply check, is a rock in that position or is there sand in that position? Finally, we're going to add a method, drop sand, to our cave that's going to allow us to simulate a single grain of sand being added. This method is going to attempt to add a grain of sand, and if that grain of sand was added, it's going to return true, saying that the cave was modified. To help with this, I'm going to recommend writing a helper method called isFinished, which takes in a position and checks if that position is falling into the abyss. If it is, it returns true, indicating that our simulation is finished. Otherwise, it returns false, indicating that we should continue running our simulation. To write drop sand, you're going to initialize a grain of sand at the origin. Then, while that grain of sand is falling, you're going to check, is my simulation finished? If it is, you're going to return false, saying that this grain of sand could not be added. If the grain of sand lands, that means we've reached a spot to add it to our cave, and we add it to settled sand. And of course, I have written a test. I recommend you write a test as well. I get my input cave. I drop a grain of sand. It should land. The first grain of sand should land. It should return true. I go ahead and print my window. It should have a single grain of sand directly beneath our start. I drop another grain of sand. It should land next to that one on the left side. I drop another grain of sand. It should go to the right. I do this several more times, each time calculating where that grain of sand should go. Eventually, I need to run this 24 times. We should be able to drop 24 grains of sand in our example before calling drop sand will return false. At this point, I check, what does my cave look like? I've taken the example from the problem description and compared it here. Go ahead, write yourself a test, get that implementation working, and as always, good luck. Here we are. We have a passing test. I hope you have a passing test. If you don't yet, go ahead and pause, and here's my solution. I spawn my sand at the top, and while that grain of sand can fall, I check, is that position in a finishing position? If it is, I exit early and return false, saying I can't add this to my cave. If I continue looping and eventually can no longer fall, I add this position to my settled sand and return true. With everything in place, we are ready to simulate our sand falling and filling up our cave. To do this, we're gonna load in our example input, parse it into a cave, and run drop sand until it reports we cannot drop any more sand. At that point, you're going to check how many grains of sand are in my settled sand set and report that number. Give it a shot. I hope all went well and you've built a beautiful sandcastle. If you're like me, you couldn't help yourself but to print out every iteration, and here that is now. And I have a beautiful little animation of my cave filling up, and I report sand 24. If you're not quite here, go ahead and pause. I'm about to show my solution. Here it is, relatively simple. I read in my example. I parse my cave. I loop while I can drop sand. Inside of this loop, I clear my console. I print my window, and I delay a slight bit just to get my animation. Finally, at the very end, I report how much sand is in my settled sand set. For my big input, I'm gonna go ahead and comment this chunk out because that input is rather big. But all that's left is go ahead and download it, cross your fingers, and if all goes well, get a beautiful gold star. At this point, I hope you've received your beautiful gold star for part 1, and I hope you had as much fun completing this puzzle as I did. Now, let's talk about part 2. In this part of the puzzle, we are now asked to simulate a cave that doesn't have an infinite bottom. Instead, it is 2 spaces below the lowest platform of your input. Unfortunately, we cannot add an infinite number of positions to our occupied set, but you can modify the logic of your isOccupied function. Think about what condition you need to add here to determine that there's an infinitely occupied space 2 spaces below your bottom location. Additionally, because you'll never have a grain of sand fall off the edge, you need to update your isFinished function. Under what circumstances should the simulation end for part 2? I hope these 2 tips are enough to help you solve this puzzle. Best of luck. Hopefully at this point you've submitted your solution and received a beautiful gold star. I hope you found this video helpful. If you did, let me know. Click that like button. If you want to see more Advent of Code guides, click subscribe so you'll be notified when they're uploaded. And as always, have a beautiful day. Keep on coding, keep on growing, and you're welcome back anytime.